You had a pointer. Yes. Thank you. Can you hear me? Oh. I'll switch, sorry. How about now? Yeah? Okay. It's a lot of light. I was hoping it's going to be dark, but no luck. So I work in Microsoft SQL Server. It's a database server. I'm working in Hekaton, which is our in-memory database. So I listened through the day. It was actually kind of funny how, from like Fabric to devices to OS, basically all of you guys work for me. That's great, awesome. But we're a database, in-memory database, so throughout the day, people said how, it's the application level taking advantage of this. And I'm going to try to cover our experience with non-volatile memory, what we see as the core scenarios. So I'm really trying to answer that question. What does it take for a memory database to have a storage experience that outcompetes traditional databases? And we are an in-memory database, and as such, our performance is really good. In DRAM, for a significant class of workloads, we get 30 times better performance than a regular database. To put this in slightly different terms, if you were to compare simplistically CPU cycles, you have to run only 3% of the CPU cycles that a traditional store runs in order to get 30x performance difference. And that's oversimplifying because that's not actually what's happening. We get benefits from concurrency as well and whatnot. But for us, really, the key is not how to get more performance. The key is how to not lose performance as we move our workloads to non-volatile memory. And the question is, what exactly is the value of non-volatile memory in our particular scenario, in our context? I'm going to define the terms a little bit. The top points there, database engines, the in-memory database are these database engines that take advantage of large memory. This is clearly known. And they store almost all of their data in DRAM. So these are constants across all databases. The rest of the points are specific to Hekaton, to our in-memory database. Our in-memory representation is different from the on-disk representation. And this is the basis for a lot of the gains. We avoid a lot of levels of indirection. It's a very lean engine because we're not concerning ourselves about what the on-disk representation is going to be. It's fully integrated with SQL Server. The user experience is the same. We share the same log, which is actually important for this discussion. We share the same logging subsystem. There's no buffer pool, no dirty writes, no write-ahead logging. We don't expect transaction to have to spill to disk. And again, this is basis for performance. In our case, we have no latches or no locks. Essentially, there's no bracket lock, no critical section, nothing of that sort. Everything is atomic, right? Interval compare exchanges is the only synchronization primitive in our engine. What in-memory databases don't do, they do not compromise on ACID properties, meaning that they have the same atomistic consistency isolation, but more important for this discussion, they have the same durability as regular databases, right? So a transaction that's committed and acknowledged to the end user is actually to be found there after a system crash, right? And like I said, significant performance, we don't hold the 30x performance gains across all workloads or even perhaps the majority, but we do have workloads where that is the case. So just briefly, because I'm going to need this information a bit later on, how does this all work? The animation is gone, but I'll try to make do. Basically, what you see there is rows. Rows that hold data. They have a header. We never write data in place. So basically, when you update a row, you create another version of the same row and with the modified columns, as it were, that have been changed by the update. So you can see two types of indices, a hash index on the right side and a range index on the left side. You can see the header holding two values, a begin timestamp and an end timestamp, which shows the range of time or virtual time in which particular item of data has been valid. So you can see, for instance, John living in Paris from time 100, time 200, and then moving to Beijing from time 200 and still being in Beijing at this time. And the rows are shared in between the indices, right? So there's a single version of the row that's pointed to by both indices and chained into a chain of duplicates depending on the index, right? There's an index on name, so you can see Susan, the rows coming from Susan being chained on that particular index, whereas an index on city chains together rows that have the same city or cities that start with the same first letter. So this is an oversimplification of how the engine works. So no updates in place is the critical aspect of this. Lock-free, so all of these data structures do not require locking. And because of no update in place, there is a garbage collection that's required. This is a little bit more of the same. Garbage collection basically is cooperative. So as transactions move through the system, they discover versions that are no longer visible to anybody, right? So they would simply see that all transactions have moved, say, past time 100. Therefore, any row that has been deleted before time 100 can now be collected. And cooperatively, as they walk through the indices, they unlink rows and then they reclaim them. So there's no garbage collection being a misnomer and not a good one. There's no spike as the one associated with runtime environments because of this cooperative garbage collection system. So that's roughly, at a high level, the execution system. And obviously, this is not the interesting part for this conversation, but how do you actually make this persistent is where we're going. Right, so far we define with an in-memory databases, and I've shown you kind of the runtime part of the Hekaton engine. So this is going to be difficult, but the first thing that we tried to put the database log, which is shared between Hekaton engine and regular SQL. We tried to put this in persistent memory. And what you see here is a comparison between two scenarios. Unfortunately, it's really kind of poor. I don't know if you can read any of this, but basically, on the left side is a base scenario, and that shows the latency of transaction commits for a synthetic workload on a RAM disk, right? So this is a system. This is as fast as it's going to run, regardless what kind of NVM block-based technology we're going to use, because again, the log is on RAM disk. And what you can see there on the top is the number of cores, 1 through 64. On the left side is the latency of different transaction commits. So this is a histogram, essentially, latency versus parallels. And compares this with the implementation of the log that is byte-addressable, right? So we stored the log, instead of storing it in traditional way, the way SQL Server does in blocks, we store it in a cache line log implementation. And what you can see is that compared to a RAM disk, the cache line implementation shifts the latency of all transactions up by, since this is an exponential scale, as a logarithmic scale, shifts the latency up by quite a bit, right? So the behavior is quite a bit better in terms of end-to-end latency for transactions. And at the bottom here, the two lines, you're going to see the throughput difference, right? The load time, so how long did it take to populate the database? And you can see differences between 50% and 36%. The PMM log being, whatever that is, 64% faster at 64 cores. And in terms of updates per second, so overall throughput of the workload, at every thread utilization point, you see a gain going between 4% and, I guess, 25% across different core utilizations. So overall, both in terms of latency based on throughput, the log, the cache line log implementation does better than the block-based one, even the ideal block-based one. And I get this question a lot even within Microsoft. People say, well, look, how can that be? We have these block devices that write in less than 10 microseconds, right? So how is it possible that a cache line implementation does so much visibly better? I hope I'll get to that in just 1 second. If I could get this to work. This is a bit of similar data. This is not TPCC, but it's a workload derived from TPCC. As far as the log behavior is concerned, it has a similar kind of characteristics. And I'm not going to be able to go through all of this in the interest of time, but what you see there in the graphs is the same latency shift. The dotted blue line is the latency with the cache line log implementation, whereas what you see, the spike is a hard drive. You can see the latency for a hard drive, a traditional SQL Server implementation on top of a hard drive being at about 16 milliseconds. The peak for the PMM implementation is around maybe 200 microseconds. And different utilization points. But here's something interesting. Look at these two. So look at these two configurations. This is the cache line log on top of a hard drive. So this is not a new implementation of a log. It's an add-on, right? We're just putting a small amount of cache line addressable persistent main memory on top of the existing log. And if the existing log is on the hard drive, you can see how the latency improves from the regular implementation on regular hard drive to hard drive plus PMM significantly. In fact, it becomes better than an SSD in terms of end-to-end latency. And obviously, the implementation that has PMM on top of an SSD is the best one, right? This one turned the tide back, and people are not going to go to hard drives because of this, but it's kind of interesting how big of an impact cache line addressability in the log has. So why is that? This cache line implementation of the log is an add-on, right? We have not changed at all. And this is applicable, I think, to most storage vendors. We haven't changed our log implementation. Basically, what we did, we added this one-to-one mapping between what we store in DRAM and what we store in PMM. So consider the thread, transaction carrying thread that has to commit, that it copies memory first to the log manager, to the regular DRAM log manager, and then does a mem copy of the same content to PMM. This is an oversimplification. This is not exactly what happens, because that mem copy, if you were to do simple mem copy, you wouldn't be able to recover the system. But in effect, it's the same thing. It copies the data twice. And then instead of waiting for the I/O to complete, it can return because it knows it has safeguarded that log content to persistent main memory, right? So basically, this is what I'm describing there. To add a new log record, we obtain a log sequence number from the regular log stream. Then we copy the existing content to the existing SQL Server DRAM log stream. Then we copy the same content in persistent main memory and atomically attach this new record to the existing persistent main memory in order to make it possible for us to recover. It's important for that persistent main memory store to be atomic, such that the states in which it can crash can be reasoned about. Right? And then, of course, on commit, we need to flush all the cache lines that are associated with a transaction. Right? So that's the implementation of the PMM log. It's fairly straightforward. It's an add-on, easy to one person for 1 month in terms of difficulty. What's interesting here that there are some consequences to this. When you do this, you don't need to force pages out to the log as frequently as you would have to do otherwise, right? Because normally in a database system, when transaction commits, when that transaction commit log record lands on a page, you're obliged to go out with that page, even if it's partially full, as quickly as possible to the log, because otherwise you affect the latency of the transaction that has committed. So you cannot do this. You have to go with partial pages. But when you've done this implementation, you can allow the page to grow to its capacity and always go with IOs that are max size, which means that your IO becomes more efficient. So although you copy the IO content in two places, in DRAM and in PMM, your trips down the OS stack are always full size, which is better for everybody, including the efficiency of the entire IO stack. Right? So that's why the IO path is shorter, then the IO blocks are larger. But you do have to modify recovery, right? Because it is possible that when you are filling your PMM memory, some transactions have committed ahead of others, and then you crashed. You had blocks that have not been filled behind blocks that have been filled. And this situation of holes inside of the log stream would not have existed in a traditional implementation, which always sends out to the IO subsystem full pages, right? So it's a situation that you need to account for. So there's no free lunch, really, but it's interesting that although you copy in two places, your overall throughput goes up, even in a system that was 100% CPU saturated when you started the experiment. So we didn't expect that behavior. So we got a log that lowers latency. Oh, and by the way, I have to mention, this is not a product plan. It's not a product announcement. None of this, I don't know if we'll ever make it. It's just discussion, right? So don't hold me to it. We're not shipping this. I know. So you have this log, and you successfully lowered the latency because you used this small amount of persistence main memory. And by the way, it's very small because actually for these experiments, 20 meg of persistence main memory to obtain this acceleration. Because really what you're covering is only the blocks that you already have in DRAM. You don't store the entire log in PMM. You just store the tail, the hot tail of the log. The stuff that gets streamed out is irrelevant. It's cold. You don't need performance for that tail end. But you got this log, which is fast now. You have a problem. How do you remote it? And I've heard the same theme coming up throughout the day. So it's kind of interesting. The way we remote it today in SQL Server is on the left side. Essentially, a log block that's ready to go to disk is put on the wire and is sent to a secondary, right? It's the same log block. And then we get a quorum from one or multiple secondaries, and and the local commit, and that's what when the acknowledgement happens back to the user. So that's the left side. But obviously, this won't work anymore because, like I said, in order to get the log performance up, you have to increase the number, you have to increase the size of these log blocks, right? So all of a sudden, what lowered your latency on log will make your HA story worse. The solution for us is to send the send the traffic from the transaction commit path, so above the log block formation. So as transactions commit, gather all of the records that pertain to one particular transaction and send them, put them on the wire immediately. This is the layer right above. Put them on an RDMA pipe and immediately send them. That would double the network traffic, but bandwidth is not the problem in an OLTP system. It's actually latency that's impossible to solve. So that adds about 25 microseconds latency to a transaction commit, but that latency, one is unavoidable, but it doesn't need to lower your throughput because that latency, you can actually fill it, and we backfill it with context-free work. Unfortunately, I think I'm going to be running out of time before I can tell you what we did for checkpoint. I don't know, open 5 minutes. Okay, so let me go and try real fast. The dark side of optimizing for memory is that putting this data on disk and reloading it is really hard. And we've done a lot of work to parallelize it, to fully utilize the entire, if you have 10 streams, load them all in parallel. Everything, every trick in the book we have applied. But still, if you have 1 terabyte and you have to load at 1 gig a second, it's still going to take you about 20 minutes to come up. And I said in the beginning that our struggle is not to improve performance of Hekaton. It's actually to not lose performance when we move to non-volatile memory. The only place where that's not true is actually in recovery. Running in non-volatile memory gives us the chance to come back instantaneously. This is because if all of those rows would be in non-volatile memory and we had a way to bring them back, we could come back immediately, not in 20 minutes for 1 terabyte, but instantly. This is one experiment that shows that even if you are trying to load the data and sort it at recovery time, it would still, you do not obtain constant recovery time unless you can save the data already sorted. And that introduces actually pressure on the programming API that has been discussed throughout the day. I wish we could sync on that. Any programming API that requires you to flush is too heavyweight to use. I don't know how to put this. Running transactions at this rate is almost impossible to have flushing APIs. The system has to save the state as it was at the time of the crash without me requiring to explicitly flush anything. Otherwise, it's simply not doable at transactional rates that we're running. I think I'm going to just run out of time because there's too much content to abuse you with. But if there are questions so far, and I can take more questions if you're particularly interested about the topic outside, but.
Well, we have a couple of questions now.
This guy's there.
Are you planning on publishing any of this stuff?
Repeat the
What's the
question.
question?
So the question is whether we plan to publish any of this stuff. I write code, so I don't, that's not really. We have MSR, we have Microsoft Research who does this, and we work with them, and they're on a different schedule. But I suspect a lot of this is publishable. Some of it has been published actually, but not the content I present here.
On what time scale would you think that this technology will get into SQL Server?
So there are a couple of constraints, I guess. The maturity of technology, maturity of the industry, of the market. And SQL Server or server products are not known for moving very fast. So that's another, but in the order in which I presented them, that's how I would expect them to show up. I would expect the log, because it benefits both Hekaton and regular SQL, to show up faster than the HA stack, show up immediately afterwards, and then finally checkpoint, being able to have a 10 terabyte database recover in constant time to show up as the last effort. But the exact timelines is hard to predict. It's because it's not only internal factors to Microsoft or SQL Server that influence that.
Thank you, Cristian.
Okay, thank you.
Our last two speakers are really, I think, lined up more with where are we going.